All right, so we have discussed about two variable model, and we assume that there is only one x which determines y, and now we will look into a more realistic model, which is which will be a multiple regression model in which there is one y and it depends on many x's, right? Which are going to be x2, x3, x4, x5, and so on, right? So this is more realistic in the sense that if we talk about the income consumption example, it's not only consumption income that determines consumption, but there are other factors which are also important and they very much determine consumption expenditure, like wealth, right? So we'll start with the simplest of the multiple regression models, in which we have two x's and one y, right? So we have seen uh, everything about simple regression, in which there was one x that determined one y. Now our y this time depends on two x's rather than one. So this is the simplest of multiple regression models. And these two x's are x2 and x3, right? Uh, as far as notation is concerned, why x2? Why not x1? Uh, because we are having the coefficient beta 2, it's a good idea to make it x2, because then we will have a beta 3 and it's better to put a x3 with it. So it becomes notationally simple to understand, and you can use subscripts easily. And for example, if somebody asks you what is beta 4, so you would understand, okay, beta 4 would be the coefficient of x4, and you would want to uh, explain beta 2 with reference to x4, beta 4 with reference to x4, right? So it becomes easy to interpret and relate the betas and the x's. So this there is no x1 here. We have started from x2. Now these betas are called the partial regression coefficients, right? And both beta 2 and beta 3, the slope coefficients, are known as partial regression coefficients. Beta 1 is the intercept, and it simply gives the mean or average effect on y of all the variables excluded from the model, although its mechanical interpretation is the average value of y when x2 and x3 are set to 0, right? And these slope coefficients, beta 2 and beta 3, are called partial regression coefficients. So I'll explain why they are called partial regression coefficients. Why partial? What does it mean? Uh, Intercept, how do you interpret it? It is simply the mean effect on y of all the variables excluded from the model. So because beta 1 is not attached to any x, it is just the intercept. And if you assume that x2 is 0 and x3 is 0, then it is only beta 1 which is left, and there is no x attached to it. So whatever the value of beta 1 is, for example 5, this means that this is the effect of all the variables which are not explicitly written in the equation on y. And of course, this error term is there. So this is random disturbance term. Now, when we switch to multiple regression, we have already seen these assumptions. So I will not repeat these 7 assumptions, but there are 2 more assumptions which are added to our list. These are no exact collinearity between x variables and no specification bias, right? So I'll explain these 2 only. So let us start with point number 8, assumption number 8. It says no exact collinearity between x variables. What does this mean? It means that x2 and x3 are not exactly linearly related. They are not exactly linearly related to each other, right? So it is the assumption of no collinearity, right? They are not exactly linearly related. Or in other words, and to be more discrete and to be more precise in terms of terminology, it is popularly known as the assumption of no multicollinearity, right? So we will talk about multicollinearity in a great detail in the next chapter, but here also I will explain it a little bit up to so that you understand what this assumption is all about. So what does this mean, no collinearity? What does this mean? It means that you cannot write like this: x2 equals 3x3, right? Or x3 equals 1 by 3x2, right? So you cannot say that x2 is 3 times x3. You cannot say that x3 is 1/3 of x2, right? If this is true, it means there is perfect collinearity. They are perfectly, x2 and x3 are perfectly linearly related. It means if you have x3, whatever values there are, you can get x2 if you know this relationship. So x2 can be derived from x3, or x3 can be derived from x2. If you have any one of them, you can get the other one, right? So this is called multicollinearity, and in fact it is called perfect multicollinearity, right? Perfect in the sense that if x3 is 2, 4 to 1, then you can write 6, 12, 6, 3 for x2 given this relationship, right? So you can perfectly and exactly get x2 from x3, right? And this is something which violates the assumption of no multicollinearity. So we assume that in our population regression function or the regression equation, we do not have x2 and x3 such that you can get one of them from the other one, right? So this is the assumption of perfect no multicollinearity, which is violated in this case because you can get x2 from x3. right? Now, you can write it like this, that what if no collinearity means that there are no set of numbers lambda 2 and lambda 3, not both 0, such that lambda 2 x2I plus lambda 3 x3I equals to 0, right? So in my case here, when I said x2 equals 3x3, x2 equals 3x3, what is lambda, right? So let me start from here. X2 equals 3x3, and let me take my x3 to the left. X2 minus 3x3 equals to 0. So my lambda 2 is 1 and my lambda 3 is minus 3, right? So this here I have got lambda 2 and lambda 3, two numbers, lambda 2 which is 1 and lambda 3 which is minus 3. I have got two numbers such that if I multiply the first number by x2 and the second number by x3 and form a linear combination of the two products, if it is equal to 0, then we say that there is multicollinearity or perfect multicollinearity. And then violation of this assumption 8 is evident, right? So this, in this case, our lambda 2 is 1 and lambda 3 is minus 3, and their linear combination is 0, right? So they have, this is one example here. You can read it. It's just same what I explained now. What does it mean? What is the meaning of no multicollinearity? You understood the concept, or you understood uh, what is the meaning of the assumption of no multicollinearity. But let us dive deep, a little bit deep, into what does it actually mean. Suppose we have consumption, and we have income, and we have wealth as three variables in consideration. X2 is income and x3 is wealth and y is consumption expenditure. And suppose this is the PRF. So we are saying that consumption expenditure is linearly related to income and wealth, and that's what economic theory tells us. But we also know that there is some interdependence between income and wealth, right? Right? So what does this mean? It means that if income and wealth are perfectly dependent, perfectly linearly dependent on each other. For example, if you are saying that all people with high income are wealthy, all people with low income are poor, right? It means that, and there is a perfect relationship. And if you have a situation in which you can say that if you know the income, you can multiply income by 10. 10 times income is equal to wealth. So for all individuals in the population, if you can say that this is true, that multiply the income of the person by 10 and you will get the wealth of that person, right? If you can say this, it means income and wealth are perfectly linearly related, right? So this can, I mean, this is perfect relationship. The relationship may not be perfect, but some relationship is there, right? So of course there is a difference between perfect multicollinearity perfect multicollinearity and imperfect multicollinearity, which we will discuss. But here, when I'm saying that 10I equals to W, it means perfect multicollinearity, right? And this practical real life example uh, lets you understand that it is quite possible that income and wealth, it is very much possible. In fact, it is true that income and wealth are related, right? The only question is how much. Are they perfectly related like this, 10I equals to W, or are they imperfectly related, right? So there is not exact linear relationship, perfect linear relationship, but of course there is some strong linear relationship, or there is weak relationship, right? These are the possibilities. Now, what is the problem if income and wealth are related? What is the problem? Why we need this assumption? We need this assumption because if this is true, 10I equals to W, if this is true, then we will not be able to assess separate influence of income and wealth on consumption. So we are trying to measure that how much does X2 affect Y, and it is this effect is contained in beta 2, and we are trying to know how much does X3 affect Y, it is contained in beta 3, whatever the value of beta 3 is, right? Now if X2 and X3 are related, we will not be able to get our beta 2 and beta 3 measure the separate influence of income and wealth on consumption, right? So we will see how this is uh, why this statement is true. Now that's the reason I just explained very quickly why do we need this assumption, right? Now I'll throw a little bit more light on this. So we have this model, and let us assume X3 is 2 times X2, and let us put 2X2 in place of X3, right? Because X2 and X3 are perfectly linearly related, and X3 is equal to 2X2. So I have put 2X2 instead of X3 here. Now if we multiply this out and take X2 common, then we get this equation. We've taken X2 common in these two terms, this term and this term, so that inside the bracket here we have only beta 2 because X2 is common and outside the bracket, and then here X2 is common, so 2 beta 3 is there, right? Now let us assume alpha equals beta 2 plus 2 beta 3, and we replace this term by alpha here, and we get this equation, yi equals beta 1 plus alpha x2 plus ui, right? So you can see that there is no need to run this regression, right? Because whatever beta 2 you will get and whatever beta 3 you will get, you can simply multiply beta 3 by 2 and add beta 2 to it to get alpha, which is the coefficient of x2, right? So alpha measures the effect of x2 on y, right? So in effect, we don't have a 3 variable regression here. We have a 2 variable regression. We don't have a multiple regression. we have a simple regression here, right? So this regression is useless because it will not give you anything. This regression is more meaningful, right? And whatever alpha you will get uh, will be equal to a combination of beta 2 and beta 3. So from alpha, there is no way you can separate alpha into beta 2 and beta 3. There is no way to do it. You can't separate the two parts of alpha, beta 2 and 2 beta 3. You can't separate them. You will get a consolidated alpha if you run this regression, right? And that means beta 2, which measures the effect of x2, which is the which is the individual effect of x2 on y, and beta 3, which is the individual effect of x3 on y, you will not get that. What you will get is consolidated alpha, which contains both the effects, the effect of x2 on y and the effect of x3 on y. So a combined influence of x2 and x3 on y is captured by alpha, right? You can't separate the influence of x2 and x3 on y. That's the problem when you have multicollinearity. You cannot separate the effect of the collinear variables, individual separate effects of the collinear variables on the dependent variable. What you would get is a combination of the effects or a consolidated effect of the two variables on y, right? So that's why uh, we need to assume that there is no multicollinearity in the population, because if it is so, it means we will not be able to measure the separate influence of the collinear variables on the dependent variable. Am I audible to all of you? Am I clearly audible, students?
Yes, sir.
All right. All right. So now multicollinearity is always there, right? Because if there are any two variables in the world, they would be at least weakly related, right? And generally in economics, we work with economic variables, and you already know, being students of economics, these economic variables are so much intertwined and interrelated. So when you are running a multiple regression of y on a number of x's, then you would find so many interrelationships, and some would be strongly related, some would be perfectly linearly related, some would be weakly linearly related, some would be related up to an intermediate level, right? So there is no guarantee that there will not be correlations among the regressors, right? So when this is so, how to go about it, we will talk this in that chapter, in the next chapter. But here we are just trying to understand the meaning, right? So we are talking about linear relationships, perfect linear relationships, when we are talking about multicollinearity. Multicollinearity does not rule out nonlinear relationships between the variables. For example, x3 may be equal to x2 squared, right? So this will not violate the assumption. it is okay, right? Because this is non-linear relationship, not linear relationship between x2 and x3. If x3 equals x2 squared, this is okay, no problem, right? We are talking about linear relationships in multicollinearity. Keep this in mind. How do we interpret multiple regression? So we have this. Let us take the expectation of on both sides, right? If we take it, if we do it, we will get this equation: expectation of y given x2 and x3 equals beta 1 plus beta 2 x2 beta 2 x3. Of course, this is 0 because the expectation of ui is 0, right? And why there is no expectation here? Because expectation of x2 given x2 is x2, right? And expectation of x3 given x3 is x3, right? So this is what we get. So we are talking about conditional mean of y, right? Conditional mean of y, and we have fixed regressors. So that assumption is already there. All the 7 assumptions are there. We have just added 2 more: no multicollinearity and no specification bias, right? So what we are trying to obtain is the mean value of y, or conditional mean of y, for given values of x's, right? x2, x3, x4, whatever x's are there. So in this sense, this is same as simple regression, because we talked about this in simple regression, and there is no difference in terms of this notation here, right? So now these beta 2 and beta 3 are known as partial regression coefficients or partial slope coefficients, right? So why partial? Question is, why partial? Because beta 2 measures the change in mean of y, change in x2, holding x3 constant. So because of holding x3 constant, we call it partial, because we are holding x3 constant. So beta 2 is partial slope coefficient of x2. Similarly, beta 3 is partial slope coefficient of x3, because beta 3 measures the rate of change of x3, rate of change of y with respect to x3 per unit change in x3, keeping x2 constant, right? So when we are keeping x2 constant and measuring effect of x3 on y, or when we are keeping x3 constant and measuring the effect of x2 on y, what we are trying to do is we are trying to get separate effects or individual effects, right? Or unique effects, whatever you call it, of a given x on y, keeping other x's out of the equation, keeping other x's as if they don't exist, right? So we are trying to measure the direct or the net effect of a unit change in x2 on the mean of y. Net of what? Net of any effect that x3 may have on y. So we want to keep x3 out when we are measuring effect of x2 on y through beta 2, right? Because beta 2 measures what is the change in y if x2 changes, if x2 rises by 1 unit. you have to add one more phrase to it. Net of x3, net of any effect that x3 may have, or keeping x3 constant, right? So that's why these are known as partial regression coefficients or partial slope coefficients, and not simply, we generally call them slope coefficients or regression coefficients, right? But in a stricter sense, being terminologically correct, we have to say that these are actually partial regression coefficients. So we can do one exercise to understand this. That if you regress, suppose you have this regression, right? Y equals beta 1 plus beta 2 x2 plus beta 3 x3 plus ui, right? In this regression, you want to get the effect of x3 on y. You want to get the effect of x3 on y, right? And you can measure it through beta 3. How to get it? So what you will do is, you will regress y on x2. Right? You will regress y and x2 in this way. And then you will regress x3 on x2. Right? Now what is this? What is this? This is part of y which is left after removing the influence of x2. Part of y which is left after removing the influence of x2, because x2's influence has been captured by alpha 2, and whatever effect x2 had on y has been removed, right? Because if you take this alpha 1 plus alpha 2 x2 on the left hand side, you will subtract it from y, and then you will get what is u1i. u1i is that part of y which is left after removing the influence of x2 on y. Right? What is this? You can interpret it in a similar way as above. You can say that u2i is that part of x3 which is left after removing the influence of x2 on x3, right? Right? So now we have y free of x2 and we have x3 free of x2, and x2 is gone, x2 is nowhere. We have y free of x2 and x3 free of x2. Now let us regress our y free of x2 on x3 free of x2. When you will do this when you will run this regression, you will get lambda 2, and you would find that lambda 2 is equal to beta 3. It will be same as beta 3. We can do this exercise. It's a simple exercise, easily in Excel, but I would want you to do it yourself because it will save us time. You can simply run these 3 regressions regression 1, regression 2, regression 3. Run these 3 regressions, you will get lambda 2, right? And then run this regression, the fourth one. And then you will see that beta 3 in regression 4 will be equal to lambda 2 in regression 3. They will be the same, right? So do it yourself. It's a simple exercise. It will take a few minutes for you to do it. Or should I show it to you right now? Or will you do it
So
yourself?
we'll try doing it on our own.
All right. All right. What about other students? What do you say? Should we move forward? You'll do it yourself. You must do it, right? Don't leave this because
Yes,
you'll do it, right?
yes, sir, we'll try to do.
Yeah, great. So run these 3 regressions and you would find this result that lambda 2 would be equal to beta 3. All right, now, uh, but these we have run 4 regressions, right? So we don't have to run 4 regressions to reach beta 3, to get beta 3. We don't have to do it. We have to run just one regression, this one, and we will get beta 3 directly. And what these 4 regressions tell us is that first we have to remove influence of x2 from y, and then we have to remove influence of x2 from x3, and then we can run y on x3 and get the effect of x3 on y in captured in lambda 2, right? So we don't have to go through this multi-step procedure because uh, this OLS procedure does exactly the same. You can simply run this regression y equals beta 1 plus beta 2 x2 plus beta 3 x3 plus ui, and you would directly get the partial regression coefficient beta 3. And this is true for beta 2 also, whatever I've explained for beta 3. You can do these 4 regressions the other way around also, and you will get beta 2 in the same way, right? So this procedure is never used, but it is explained in books just to drive home the true meaning of partial regression coefficients, because here you can see that effect of x2 was removed from y and x3, and then what remained of y and what remained of x3 were regressed, and then we got the effect of x3 on y. So in that sense, this makes us understand that beta 3 is actually partial regression coefficient, right? So it drives home the meaning of partial in this whole term, partial regression coefficient. So that's why it was done. Now, let us talk about the estimation part a little bit here. This is our PRF. This is the regression which is there in the population, and we want to get an estimate of our betas from as per this regression, right? So we have to write a SRF. We can write our SRF like this. You can see that these are the sample statistics uh, because they have a hat, and then we have residuals UI hat. So notation is same, right, as we had in simple regression. So there is nothing new here. So I don't have to explain this again. And then we can start our OLS procedure in the same way as we did before. What we need is to minimize the sum of squared residuals. That's the method of OLS, right? And that's what we will do here. To get the residual, we can simply take UI hat to the left, and then whatever is there, we can take to the other side. So we'll have yi minus beta 1 hat minus beta 2 hat x2 minus beta 3 hat x3. This we got from this equation, and then squaring it means we have squared it, and then there is a summation because we have to sum it also. So writing an equation for summation ui hat squared would be easy from here, right? So this is our equation, and then minimize it. So minimization means you have to differentiate it partially with respect to beta 1 hat. What you're differentiating? You are differentiating summation ui hat squared. You will get equation 1 differentiated with respect to beta 2 hat, the same thing. You will get equation 2, and then partially differentiate with respect to beta 3 hat, the same thing. Sum of squared residuals, you'll get an equation 3, right? And those three would be the three normal equations. So these are equation 1, 2, and 3 that we will get by doing this partial differentiation. And these are normal equations as we got in simple regression also. So procedure is same. Procedure is same, exactly same, right? So do it yourself and get these three equations by differentiating this thing with respect to beta 1 hat, beta 2 hat, and beta 3 hat, right? Once you got these three equations, you can see that there are some unknowns that you want to get. You can use Cramer's rule, you can solve them simultaneously as you wish, but you have to get three things from here, from three equations, three unknowns. And these three unknowns are beta 1 hat, beta 2 hat, and beta 3 hat. So you can see that there are three unknowns, beta 1 hat, beta 2 hat, beta 3 hat, three unknowns, three equations, easy to get, right? Three unknowns, beta 1 hat, beta 2 hat, beta 3 hat, in terms of x's and y's, right? All others are x's and y's, right? Y bar, x bar, summation x2, summation x3, summation x2 squared, summation x2 times x3, summation y times x2, summation y times x3. So all other terms will be there as they are. You just have to solve for beta 1 hat, beta 2 hat, and beta 3 hat. You are solving three simultaneous equations for three unknowns, right? You can use Cramer's rule as we did before, which will be easier, or you can solve them simultaneously using algebra. You will get three equations for the betas, and these are the results that you will get, right? So we can derive this also. First you try yourself, then I will show how to derive. I think this derivation will be given in the book. If not, I will do it for you. So try it today. Try to get these three equations of the betas. Now the variances. Of course, here proofs are required. Here also proofs are required. How to get the variance? We will prove it later. Right now, these are the variances of the three betas, and you understand the concept of variance of an estimator, right? Or standard error, standard deviation of an estimator, right? So these are the variances of the three betas. If you just have a close look on it, you can see there are x's on the right side. X's, small x's. Small x means deviation. Capital X I minus x bar. So these are all the x's, and we have our sample data. So these are all, we already have these things from our sample, right? So these are known things. This is something new. This is something we don't know, sigma squared, right? That was the case before also. So we need to understand a little bit better what is this sigma squared. Once we get this sigma squared, we can easily get variance beta 1 hat, variance beta 2 hat, and variance beta 3 hat, right? This is a more simpler formula for the variance of the slope coefficients. It seems very small as compared to these two, right? So we'll see how to get this formula from here later. So let us stop here. We will continue next time from here. If you have any questions, you can ask.